Hello everyone. Today we are going to start a new course on differential calculus, and we are going to learn about functions, limits, continuity, maxima, minima of one variable, and how to draw curves, how to see its concavity, and so on. Okay, so today we are going to take our first lecture on defining different functions. Okay, and in this lecture today we are going to talk about the definition of a function, then the vertical line test to check whether a graph can be written as a function or not, uh, what are increasing and decreasing functions, what are odd and even functions. Then we will define some common use functions, and what is the shift and scaling of functions, and one-to-one functions, and the horizontal line test. So we can also define then the inverse of a function. Okay, so the first definition that we are going to take today is we are going to define what exactly functions are. Okay, so function f from a set D to a set Y is a rule that assigns a unique single element f of x belongs to y to each element x belongs to D. Okay, so you are given say a set which we name as D, and we call it a domain set. Okay, so it's like a set from where you will take your input elements. Okay, and then we define another set Y, which we call the codomain, and whatever elements we take from domain, then using that function it corresponds, or it assigns, uh, the function assigns a unique single element in the codomain. Okay, so for every x here in the domain, there is a rule which take this element to a unique element in the codomain. Okay, so f of x are the elements here in the codomain. Okay, so if for every input there is some output, and that output is a member of the codomain. Okay, so the set D of all possible input values is called the domain of the function. Okay, so whatever values are there in the input is your domain of function. Okay, and for each element here, by rule, they will be assigned a unique value in the codomain, which we call the uh, output region, or the codomain region. But codomain may have some more elements which are not coming from the domain. Okay, so particularly those elements which are coming from the domain, those elements will also form a set, and we'll call it a range. Okay, so range is a subset of the codomain. Okay, so the set of all output values of fx as x varies throughout D is called the range of the function. Okay, and the range may not include every element of the codomain or the set Y. Okay, so the range set is a subset of the codomain. Okay, and so finally, when we define a function as this, y is equal to f of x. Okay, so where x here are the elements from the domain or input, and with this rule f of x, we generate a unique single element y, or we call it f of x, which are elements of the codomain or the range set. Okay, and the domain, if it is not stated explicitly, or it is not restricted by context, then the domain is assumed to be the largest set of real x values for which the formula gives real y values. Okay, which we call as natural domain. Okay, so if you are not if the domain is not defined, then the natural domain we can assume is the all real values x, such that we get the output as real values. Okay, For example, let us see for some of the functions, let us see what is their domains and codomains. Okay, say for example you are given a function y is equal to x square. Okay, and domain is not defined, range is not defined, so how you can check? Okay, so for all x values for which this function is defined. Okay, so this function is defined for all x from minus infinity to infinity. Okay, so the domain becomes the complete real line, and for every x value this is squared. Okay, y values. Okay, so if for positive values it is positive, for negative values also it is positive. Okay, and at x is equal to 0 it will be 0. Okay, so y values will be from 0 to infinity, which becomes the range of the function. Okay, so the domain of this y is equal to x square is minus infinity to infinity, and range is 0 to infinity with 0 included. Okay, closed at 0. Okay, say we have a function y is equal to 1 by x, then the domain of this function will be values all x except x0, because at x0 y becomes infinite. Okay, so the domain will be all x values except the value at x is equal to 0. So it is minus infinity to 0 and together with or union with 0 to infinity. Okay, so x is equal to 0 is not included in the domain. Okay, and the range will be all y values corresponding to this domain. So y is also minus infinity to 0 and 0 to infinity, because when x because x can be written as 1 by y, so y0 is also not part not come as a output. The third function is say y is equal to root x. Okay, so domain of this function will be only the positive values for x with x equal to 0 also included. So domain is 0 to infinity with 0 included. Okay, the negative values will not be part of domain, because then y becomes y will not be real. Okay, and the range is the output values. So for every value in the domain it will give only positive values, and 0 at x is equal to 0. So range is also 0 to infinity. Okay, say 1/4 is y is equal to root of 4 minus x. Okay, so those values of x which keeps this value 4 minus x positive. Okay, so that will be whenever x is less than 4, or x is equal to 4 will make it 0. So x is less than equal to 4, so that means domain is minus infinity to 4. Okay, so and if you substitute any value from here, then this will be positive, so root will be positive, or it will be 0 when x is 4. So range is 0 to infinity. Okay, and say one last example is say y is equal to root of 1 minus x square. Okay, so again the domain will be all values of x for which this term inside root is positive. So when 1 minus x square is positive, that will be when x square is less than 1, or x lies between minus 1 and 1. Okay, so that makes its domain. Okay, so any x value outside this will make this as negative of root, so it will become imaginary. Okay, and for all values of x between minus 7 and 1, the root value will be between 0 and 1. Okay, so it's for any x between this square will keep the value maximum to 1 or less than 1. So this difference will be 0 or up to maximum 1 when x is 0. So square root will be between 0 and 1. Okay, so range is 0 and 1 with 0 and 1 included. Okay, so this is how we can find the domains and range of a function. The next is that we can draw the function as a graph in the xy plane. If you are given y is equal to f of x function, then you can plot in 2D with x-axis horizontal, y-axis vertical, and you can draw the graph of a function. Okay, but if in reverse I see that you are given a graph, whether that graph corresponds to some function or not, then this vertical line test will tell us whether we can say that that particular graph is for a function or not. Okay. So a function f can have only one value of fx for each x in its domain. Okay. So for every input there will be only one output. Okay. That's how function is defined. Okay. So if you are considering a vertical line, okay, so that vertical line will cross x-axis at one point, so that point will be the input point. So that vertical line should not cross the curve at more than one point. Okay, because for that input there should be only one output. If it intersects the graph at more than one point, then definitely that graph cannot correspond to that function. Okay, because for that one input there will be more than one output. So say if a is in the domain of the function, then the vertical line at x is equal to a will intersect the graph of f at a single point, which is a comma f of a, the function value at a. Okay, so if it is also intersecting at some other point, then that graph is not graph of any function. Okay, say for example this is a equation of a circle, unit circle. Okay, so if you take any vertical line uh, passing through the domain of this circle, okay, then you see that if say this point is in the domain, and so it is say at x is equal to a, then correspondingly this line is, you can see that it is intersecting the circle at 2 points. Okay, and so for x is equal to a input, we are getting two outputs, two y values here. So this graph cannot be a graph of a function. Okay, so the circle is not the graph of a function as it fails the vertical line test. Okay, so if you are given any curve or any graph in general, then what you can do is you simply take a vertical line, move it from left to right, and see that at any point it touches that curve at more than one point. If it touches the graph at more than one point, then that graph cannot be a graph for a function. Okay, see you are given only a curve which is a semicircle. Okay, upper semicircle. Then if you take any vertical line and move it from left to right, then at any x value it will only touch at one y value. Okay, it will touch graph at only one point. So this graph satisfies the vertical line test, so it is the graph of a function. Okay, similarly the lower semicircle is a graph of a function because it satisfies the vertical line test. Okay, the third thing that we are going to discuss here is that the piecewise defined functions. Okay, so sometimes the functions may not be defined by a single formula like y is equal to fx. Okay, the fx may be divided into pieces to generate the curve. Okay, for example the absolute value function, which is generally written as y is equal to modulus of x, is actually a piecewise function. Okay, because the graph of this function is this blue. Okay, so for x less than 0 it is a this curve with slope -1, and for x greater than equal to 0 the curve is this. Okay, so there are two pieces here, one this piece and this second piece. Okay, so for this function can be defined in a piece into pieces like this, that modulus of x is takes value x when x is greater than equal to 0, so it's like y is equal to x line, and it takes minus of x when x is less than 0, so it's like y is equal to minus of x line. Okay, so this single function y is equal to modulus of x is actually uh, 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 sum of two pieces, y is equal to minus x line and y is equal to x line. Okay, so immediately the domain is minus infinity to infinity, because this we can take any value of x. Okay, it is defined for all x. Okay, and range is 0 to infinity with 0 included. Okay, because the y values are always positive. Okay, say take another example. Say given a function fx is equal to this. Okay, so it takes value minus x when x is less than 0. It takes value x square when x varies from 0 to 1, and it is 1 when x is greater than 1. So basically function is defined into pieces with three curves. One is like y is equal to minus x line, then y is equal to x square curve, and then y is equal to 1 line. Okay, so and for each there is a restricted domain. Okay, so the total domain of the function is where this whole x is defined. So x is defined for all x less than 0. So minus infinity to 0, then 0 to 1, then 1 to infinity. So domain becomes minus infinity to infinity, and for each x value we get how many y values. Okay, so when x is less than 0, this is a positive number, where x between 0 and 1, this is also positive, and for y greater than 1, this is already 1. Okay, so the range is 0 to infinity. Okay, so if we draw this first curve, y is equal to minus x, where domain of this is minus infinity to 0, then from 0 to 1 it is y is equal to x square curve, and then when x is greater than 1, it is y is equal to 1 line. Okay, so you can see that y is always positive. Okay, so the range is 0 to infinity. So we can also define like different pieces of function in different domain. We can combine and write a function, a new function. Okay. Then increasing and decreasing functions. Let f be a function defined on an interval I, and let x1 and x2 be any 2 points in the interval I. Then if the function value at x1 is less than function value at x2, whenever x1 is less than x2, then f is said to be an increasing on I. Okay, so if x2 is greater than x1, that means on the real axis, if there is a point which is greater than the previous point, then the function value corresponding to x2 is greater than the function value corresponding to x1. Okay, so the height is increasing as we move from left to right, then the function is increasing function. Okay, if the reverse trend happens, then the function is decreasing function. That means if function value at a lower point is greater than the function value at at the second point, right point, whenever x1 is less than x2, means x2 is on the right. Okay, then function is decreasing on I. Okay, so let us understand this by the same graph that we did previously, a piecewise function. Okay, so in minus infinity to 0, if you take any 2 points, say x1 at minus 2 and x2 at minus 1, okay, so this x2 is greater than x1, the function value corresponding to minus 1 is here, which is 1, and function value at minus 2 is minus 2. Okay, so function value at x2 is less than the function value at x1. This height is less than this height. Okay, so it satisfies the second result, and the function is decreasing function here. Okay, and say in this second between 0 and 1, if I take 2 points x1 and x2, then for x2 greater than x1, the height is bigger than this height. Okay, so function is increasing here. Okay, and if I take any value for x greater than 1, say x1 and x2 are both greater than 2 with x2 on the right, then the function values are same. Okay, so the graph is not increasing, the graph is not decreasing, so it is neither an increasing function nor an decreasing function. There are strict inequalities here. Okay, so this trend holds. Okay, the function is decreasing on minus infinity to 0. Okay, the function is decreasing. Okay, so for any 2 points in from minus infinity to 0, okay, if you take, then the value of function at the right point will be less than the value of function at the left point. Okay, the function is increasing in 0 to 1. So if you take any 2 points in 0 to 1, the value of the function at the right point will be greater than the value of function at the left point. Okay, and the function is neither increasing nor decreasing in 1 to infinity. Okay, in this region, take any 2 points, the heights are same. Okay, so this is how we define increasing and decreasing functions. Then even functions and odd functions, and this is a very important has a very important property. Okay, so first is that a function y is equal to fx is said to be even function of x if it satisfies that f of minus of x equals f of x for every x in the domain of function. Okay, so for every x in the domain of function, if this result is satisfied, okay, if I replace x with minus x and calculate the function value, then the function value remains same, then the function is said to be even function. Okay, and a function y is equal to fx is an odd function of x if f of minus x equals minus of fx. If this result holds, then for every x in the domain, then we say that function is an odd function. That means if I replace x with minus x, then function value at minus x is negative of the function value at x. Okay, then the function is a odd function. Okay, so this has important property that whenever the function satisfies this, that the function value at x and minus x are same, say there is a x point, then the corresponding minus x point will be here. So the if the height at x and height at minus x, they are same, okay, for all x in the domain, okay, then the function is even function. And this is one of the important properties for even function, that it is symmetric about the y-axis. Okay, so there is a symmetry about the y-axis. The graph of the function is symmetric about the y-axis if function is a even function. Okay, similarly, if function is odd, then it has a property that the graph of the function is symmetric about the origin. Okay, right, so at any x value, if the function height is y, then the minus x value, the function value will be minus of y. Okay, so upward function will be downward function here. Okay, it's a symmetry about the origin. Okay, now I'll discuss some of the common functions that are used. And first function is the linear function, which in general is defined as this equation f of x is equal to mx plus b, where m and b are constants, and in particular if b is 0, then this will be y is equal to mx, and these will be straight lines passing through the origin. Okay, and in particular this m is the slope, and in case this m is equal to 1 and b is 0, then y is equal to x is a straight line passing through origin, also called the identity function. Okay, when the slope is 0, that means m is 0 and b is also 0, then the resultant is a y is equal to 0 line, which is x-axis. Okay, and if b is non-zero and slope is 0, then it will be y is equal to b. Okay, for different values of b, this is a constant function, y is equal to constant. Okay, so say I just draw a few lines, say with the b0 and m1, it will be y is equal to x line, so it's a straight line passing through origin with slope 1. Okay, y is equal to minus of x line, so slope is minus 1 and b value is 0. Okay, so this line passing through origin is slope minus 1. This is a line with the slope 1 and b value plus 2. Okay, so we'll talk about this in next few slides, that how this curve is shifted to up or down or left or right. Okay, and similarly we can have, say, with slope minus 1 and b value plus 2, this line, okay, with a negative slope. The second type of functions are power functions, which are defined as a function fx is equal to x power a, where a is a constant. Okay, so they are called power functions. And now we can discuss it with three cases depending upon the value of a. Say if a is a positive integer, like a is 1, a is 2 and so on, then it is like y is equal to x power 1, or y is equal to x square, y is equal to x cube, y is equal to x4. Okay, so those type of curves. So I'll just draw y is equal to x square will be this curve. Okay, y is equal to x cube is this second curve, y is equal to x power 4, y is equal to x power 5, and so on. Okay, so what interesting we can see from here is that when n increases, x square, x cube, x4, x5, how the curve tend to get flat towards the x-axis. Okay, so you can see at x is equal to 0, the curve touches the origin, and at x is equal to cube, at x is equal to 4, at x power 5, you see that the curve starts to get flattened. So if you can power x power 6, x power 7, you will find that it gets more and more flat on the interval -1 to 1. Okay, and rises sharply when x is greater than 1 or x is less than -1. Okay, and each of these curves uh, passes through origin, and also they passes through the point 1 1. Okay, so because x is equal to 1, y value will be 1 for each of them. So all these curves pass through origin and pass through the point 1 1. Okay, the curves for even power x square, x4, x6, x power 8, they are symmetric about y axis. They are even functions. Okay, and the curves x cube, x5, x power 7, and so on, they are symmetric about origin. So they are odd functions. Interestingly, you can also see that whenever you have even powered functions, they are decreasing in minus infinity to 0. Okay, decreasing in minus infinity to 0, and then increasing in 0 to infinity. Okay, so they are decreasing for all x less than 0, and they are increasing for all x greater than 0. uh, and what about the odd functions like x cube, x5, x7, so on? They are always increasing. Okay, from minus infinity to infinity, they are increasing functions. Okay, now take another the second case when uh, a takes say negative integer values, like a takes -1 value or a takes -2 value. So we'll have y is equal to 1 by x curve, or y is equal to 1 by x square curve, and so on. Okay, so like this is y is equal to 1 by x when a is -1. Okay, or you have when a is -2, you have curve y is equal to 1 by x square. So in the first case, you see that the domain is all x except at x is equal to 0. Okay, so all real values of x except x equal to 0. So x is not equal to 0 is the domain. Okay, because at x equal to 0, the function is not defined. The range is also y not equal to 0. Okay, so y cannot take 0 value. All other values y can take. Okay, the curve is symmetric about the origin, and it is decreasing from minus infinity to 0. Okay, and decreasing from 0 to infinity. Okay, so the curve is symmetric about origin, and it is decreasing from minus infinity to 0 and 0 to infinity. Similarly, if you look at this curve of 1 by x square, again the domain is that x cannot be 0. Okay, and a range is that y is positive. Okay, so range is y varies from 0 to infinity. Okay, the curve is symmetric about the y axis, and it is increasing in minus infinity to 0 and decreasing in 0 to infinity. Okay, the third possibility is that the a values are the fractions, like 1 by 2, 1 by 3, 2 by 3, and so on. Okay, so say if a is 1 by 2, that means it will be a root x curve. So that will be this curve y is equal to root x. Okay, or a is say 1 by 3, then this is the uh, third root of x. So this curve. Okay, so for a uh, even root, second root, fourth root, and so on, the domain will be only from 0 to infinity. Okay, and range will also be 0 to infinity. For cubic root, the domain is minus infinity to infinity, and range is also minus infinity to infinity. Okay, so as it moves, it will tend to go up, and this side it will tend to go down. Okay, right. So this is about power functions. Then next is polynomials. Okay, so a function p is a polynomial if we write p as this function. Okay, an x power n plus an minus 1 x power n minus 1 plus so on plus a1 x plus a naught, where n is a non-negative integer, and these a naught, a1, a2, so on, an minus 1, an, they are real constants. Okay, so say for when like n is 1, then this will be like ax plus b type. Okay, so it's a linear uh, curve, or it's a straight line. Okay, if n is 2, then it will be like a second degree polynomial. Okay, and so on. Okay, so all polynomials have domain minus infinity to infinity. Okay, so that's one important thing to note. Okay, say for example there is a cubic polynomial with n value 3, so highest power is x cube. Okay, so cubic polynomial. Okay, so its graph is drawn here, so its domain is minus infinity to plus infinity. Okay, second is, say this is a polynomial of degree 4, so again its graph is drawn here, and there is a polynomial again here, and its graph is again drawn here. Okay, so what is interesting to note is that there are some points where curve changes direction. Okay, so in future lectures we will also talk about this, how to calculate these points where the curves will change direction. Okay, how is the concavity of these curves, what are the points of this maxima and points of minima. Okay, so these things we will talk about. Again, in this last curve you will see one important thing, that uh, we said earlier that when we talked about function y is equal to x square, y is equal to x4, y is equal to x6, then how the curve tend to flatten near the axis. Okay, so you see that x minus 2 power 4. Okay, so at point x is equal to 2 there is a fourth power, so you see at near x is equal to 2 how the curve has flattened. Okay, similarly x plus 1 power 3, so near x is equal to minus 1 point there is a third power. Okay, so near x is equal to minus 1, you see this how the curve has flattened here. Okay, and at x is equal to 1 there is a 1 power. Okay, so near x is equal to 1 it is not that flat. Okay, similarly when x is 0 you can easily calculate what is the y value, so that this value, how we locate that on one side the curve is going this is decreasing, then this is increasing. So we'll talk in future lectures how we will know that in what region the curve is going to decrease, in what regions the curve is going to increase, and how to sketch these curves. Okay, given this function how we can sketch this curve. Okay, so this is that this all this will be part of our this differential calculus course. Okay. Okay, the next are the rational functions. Okay, a rational function is a quotient or ratio of this form. Fx is written as px by qx, where p and q are both polynomials. Okay, the domain of rational function is the set of all real x for which the denominator is non-zero. Okay, the denominator is qx, so qx is non-zero. Okay, so for all those x. Okay, so domain of polynomial is minus infinity to infinity. Okay, so this polynomial is also domain is minus infinity to infinity. Okay, but this curve may be passing through the x-axis, so all those points. Okay, uh, where this denominator becomes 0, those will not be part of the domain for this rational function. Okay, So for example, y is equal to this 2x square minus 3 over 7x plus 4. So it's a polynomial by polynomial. So its domain is all x points except where 7x plus 4 is 0. Okay, so x is equal to minus 4 by 7 is not in domain. Okay, so that's the point here. Okay, x is equal to minus 4 by 7. This point is not in the domain. Okay, and then we can draw the curve from this rational function. Okay, similarly, given another function polynomial by polynomial, okay, we can draw the geometry. Okay, and the domain of this is everywhere except denominator equal to 0. So no real value of x will make the denominator 0. So domain of this function is minus infinity to infinity. So you can see the domain is minus infinity to infinity. Okay, and similarly this polynomial by polynomial. Okay, so domain is every x except the points where the denominator is 0. Okay, so that's this point. Okay, so here you can see that some red lines are drawn. Okay, these red lines are the asymptotes. Okay, so we'll also talk about how to calculate these asymptotes and what exactly asymptotes are. So we'll talk about this in future lectures. Okay, in this course only. Then algebraic functions. Okay, so any function constructed from polynomials using algebraic operations like addition, subtraction, multiplication, division and taking roots lies within the class of algebraic functions. Okay, all rational functions are algebraic. So say for example y is equal to third root of x into x minus 4. Okay, so this function is uh, built by taking a x then its root and multiplying with another polynomial. Okay, so you can take root, you can multiply with another polynomial. So x its third root and then you multiply with a polynomial x minus 4. Okay, so this comes as a algebraic function because it is constructed using polynomials by using roots, multiplication. That means algebraic operations. Okay, like this function is a polynomial and it's a polynomial is squared and third root. Okay, so this function is an algebraic function. Okay, so it's again a product of polynomial with the second function being taken squared and fifth root. Okay, so uh, one interesting phenomena again you can see from here is that uh, 1 minus x powered 2 by 5. Okay, now here the root is bigger than the power. Okay, so you can see that what happening at x is equal to 1. Okay, the curve tends to become vertical instead of flattening. Okay, so instead of flattening at x equal to 1 it tends to be vertical at x equal to 1. Similarly here at x is equal to minus 1 and 1. Okay, the curve tends to be a bit vertical. Okay, because the it's a third root and only second power. Okay, similarly you can see at x is equal to 0 this is a 1 by third power. So at x is equal to 0 the curve trying to be a bit tending towards the vertical. Okay, similar trends. Okay, so when there is a positive power like x square, x cube, x4 or x minus a power 10, then at x is equal to a you will find that curve tends to flatten. Okay, but if there is a square root, third root, fourth root, then the curve tend to become vertical. Okay, okay. Then there's another class of functions which are called trigonometric functions. Okay, the graph of six basic trigonometric functions. You know the six basic trigonometric functions are sine of x, cosine of x, tangent of x, cosecant of x, secant of x, and cotangent of x. Okay, so first is the graph of y is equal to sine x function. Okay, and this function has a domain minus infinity to infinity. Okay, and range minus 1 to 1, and the function is periodic with the period of 2 pi. Okay, by periodic we mean that the function tend to repeat after this length. Okay, so say at x equal to 0 if I start then this curve when it reaches 2 pi, this length is 2 pi, okay, one period. Then after this the curve repeats itself, okay. So periodic means that the function repeats itself after this period, okay. And the range you can see is -1 to 1, okay. So this height is maximum 1 and -1, okay. And domain is all x, so it's defined for all x, okay. Then you have a y is equal to cosine of x function, okay. Its domain is again minus infinity to infinity, range is -1 to 1 and periodic with period of 2 pi, okay. So this curve is just a shifted curve of this with a pi by 2, okay, angle. The y is equal to tangent of x. This function is having domain all x except the plus minus pi by 2, plus minus 3 pi by 2 and so on, okay. So and at plus minus pi by 2, plus pi by 2 etc., this function is not defined, okay. So domain is all x except these points. Range is minus infinity to infinity, okay. So it takes all values from minus infinity up to plus infinity, and the period of function is pi, okay. So from, say for example, minus pi by 2 to pi by 2, this curve, and then it repeats itself, okay. So this length is pi by 2 plus pi by 2, so this length is pi, x value is minus pi by 2 to pi by 2, okay. So periodic with period of pi, okay. Then the cosecant function, okay. So y is equal to cosecant of x, and we know that cosecant of x is 1 by sine x, okay. So immediately you see that domain is all x, okay, except the points where sine x becomes 0, okay. Sine x becomes 0 at minus pi, 0, pi, 2 pi, okay. So those points are not part of domain, okay. Yeah, right. Cosecant x is 1 by sine x, and we know that if you have a function by function, then domain is all points where denominator is non-zero, okay. And because sine x is 0 at 0, pi, 2 pi, so those points cannot be part of domain for this function, because this is 1 by sine x, okay. And because the range is -1 to 1, and then this function is 1 by of this, so range of this will be all points greater than 1 or all y less than -1, okay. And it is again periodic with a period of 2 pi, okay. So you see this curve, then this curve, then next will be again a curve upward, okay. So this will start repeating, okay. So 2 pi is the period. Similarly, y is equal to secant x, and we know secant x is 1 by cosine x. So again, domain will be all points except those where this cos x becomes 0. So at minus pi by 2, pi by 2, 3 pi by 2. Okay, so minus pi by 2, pi by 2, 3 pi by 2, minus 3 pi by 2. Okay, so all these points are not in domain, all other points are there. Range is, because its range is between -1 and 1, and this function is reciprocal of this, so range of this is y less than equal to -1 or y greater than 1, okay. Period is again 2 pi, okay. And similarly, cotangent function is 1 by tan function, okay. So again uh, the points where this function becomes 0, okay, those points cannot be domain, part of domain here, okay. So it will be like 0, pi, minus pi, okay. So 0 plus minus pi plus minus 2 pi, they are not in domain of cotangent theta, okay. And the function has a range of minus infinity to infinity, okay. And the function is periodic with a period of pi, okay. So this is about the trigonometric functions. And then we have exponential functions, function of the form fx is equal to a power x, where the base a is positive constant and a is not equal to 1, are called exponential functions, okay. All exponential functions have domain minus infinity to infinity and range 0 to infinity. So the exponential functions never assume the value 0, okay. So this is important, the domain is minus infinity to infinity, range is 0 to infinity, and exponential functions never assumes the value 0. Say for example, there are few exponential functions drawn here, okay. So this is y is equal to 2 power x, y is equal to 3 power x, y is equal to 10 power x, and here with a negative exponent, y is equal to 2 power minus x, y is equal to 3 power minus x, y is equal to 10 power minus x. Okay, so exponential functions with positive values of a, they are increasing functions. Okay, and they never become zero. Okay, and exponential functions with a uh, these 10 power minus x, 3 power minus x, they are decreasing functions of x. Okay, and they never uh, touch x-axis. Okay, so they never assume the value 0. So you can see that the domain is minus infinity to infinity, but the range is only 0 to infinity. Okay, the natural exponential function is denoted by e power x with the base e uh, is known to have value 2.71828 and so on. Okay, so uh, terms are never ending. Okay, the advantage of using this exponential function as a this natural exponential with e as a base is that it simplifies many calculations in calculus. Okay, so instead of using a power x with a different values, usually we use a as e. Okay, and uh, which is a natural exponential function. Okay, one of the important fact is that if you draw the graph of this e power x where e is 2.71828 and so on, okay, take that value, then that graph will also be somewhere between this blue line and red line. Okay, here. Okay, okay, so 2 power x, 3 power x, that will be 2.718 power x. Okay, so the line will be somewhere here. Okay, the important fact is that the slope is 1 when it crosses the y-axis. Okay, if you calculate the slope here for all these curves, okay, the slope of this natural exponential at on the y-axis is 1. Okay, which gives us the advantage of calculating many things. Okay, second thing to note is that this function y is equal to e power say kx, where k is any constant, also tells us about the exponential growth if k is positive or exponential decay if k is negative. Okay, so it's a very important function which is used a lot in calculus. Okay, the next are logarithmic functions. Okay, these are the functions written in this form: fx is equal to log to the base a x, where base a cannot be equal to 1 is a positive constant. They are inverse functions of the exponential functions. Okay, so domain of logarithmic functions are 0 to infinity, and the range becomes minus infinity to infinity. Logarithmic functions to the base e are natural logarithmic functions, and functions to the base 10 are called the common logarithmic functions. Okay, so again the different curves for logarithmic functions are given here with base 10, base 5, base 2 and base 3. Okay, so if you have a base 10 log function, this yellow curve, this is a common logarithmic function. But if we draw a y is equal to log base e of x, that is a natural logarithmic function. Okay, for the natural logarithmic function, uh, if we set y equals log base e of x. Okay, so if we in particular set x is equal to e, then natural logarithm of is equal to 1. Okay, so that is one of the important properties. And then the we also define these transcendental functions. Okay, so these are the functions that are not algebraic. Okay, so we already said that they are defined algebraic functions, that means all those functions which are made from polynomial functions. Okay, so transcendental functions which are not algebraic. Okay, so they include trigonometric, they include inverse trigonometric, exponential, logarithmic functions, or many other such functions. Okay, then talk about the shifting a graph of a function, and first is the vertical shifts. Okay, so if you have y is equal to fx function, then if I add a k to it, okay, so and write y is equal to fx plus k, then this shifts the graph of the curve y is equal to fx by a quantity equal to modulus of k. And what type of shift is that? Shifts the graph of f upwards by k units if k is positive. Okay, if k is positive, then y is equal to fx curve is shifted k units upward by using or adding a constant k. Okay, and it shifts the graph downward by um, k units. Okay, so if k is negative, then it shifts by modulus of k units downwards. Okay, say for example, given y is equal to x square curve denoted by this blue curve, then uh, if I add a positive k plus 1 plus 2, then it shifts the graph upward by uh, 1 unit or 2 unit depending upon what is the value of k added. Okay, and if k is negative, say k is minus 2, okay, then y is equal to x square minus 2 is a graph of parabola. This y is equal to x square shifted downward with a length of 2 units. Okay, shifted downward with length of 2 units. Okay, so basically if you add any constant to y is equal to fx, okay, on the right hand side with fx plus k, then it shifts the graph upward or downward. Okay, horizontal shifts. Okay, so if you change x to x plus h, okay, then y is equal to fx curve. If you write x as x plus h, then it shifts the graph horizontally, and it shifts the graph of the function towards left by h units if h is positive, and shifts it to the right with the length of h if h is negative. Okay, say again you are given this parabola y is equal to x square. So if you add a 3 here and make it x plus 3, then it will be y equal to x plus 3 square. Okay, so if that positive number shifts to left, okay, so this curve shifts 3 units to left. Okay, and if h is negative, say if I subtract say minus 2, then it shifts the curve 2 units to the right. Okay, so changing x to x plus h shifts the function left if h is positive, shifts it to right if h is negative. Okay, then we have vertical and horizontal scalings and reflecting formulas. Okay, for c greater than 1, the graph is scaled. Okay, and how it is scaled is that if there is a curve y is equal to fx, and if I multiply fx with c, okay, so y is equal to c times fx with c greater than 1, then it stretches the graph of f vertically by a factor of c units. Okay, and if I multiply with a 1 by c, then it compresses the graph of f vertically by a factor of c. Okay, so if c is greater than 1, and if I multiply by c, then it stretches the graph vertically. Okay, and if I multiply with 1 by c, then it compresses the graph vertically. Okay, for example, you are given a curve this y is equal to root x. Okay, and if I multiply by 3, 3 is a number, c is 3 which is greater than 1, and if I multiply with 3, then 3 times root x means it will stretch the graph vertically upward. Okay, it will stretch the graph vertically. Okay, and if I multiply with say 1 by 3 with c or equal to 3 greater than 1, then it will compress the graph vertically. Okay, so if I multiply with 1 by 3 to this root x, then it will compress the graph vertically. Okay, so this yellow curve is for 1 by 3 root x. Okay, similarly, if we scale x to cx, okay, instead of multiplying with c the whole function, if we just scale everywhere x is replaced with c times x. Okay, so y is equal to f of cx compresses the graph horizontally by a factor of c, and f of x by c stretches the graph horizontally by a factor of c. Okay, so if you are again given a root x curve, then y is equal to root 3x. Okay, so x is replaced with 3x, then it compresses the graph horizontally by a factor of c, and if x is divided by 3, then it stretches the graph horizontally by a factor of 3. Okay, and finally for c is equal to -1, okay, the graph is reflected. Okay, if c is -1, then y, and if I multiply calculate c times fx, then it will be y is equal to minus fx, then it reflects the graph of f across x-axis. Okay, and if I multiply f of cx with c minus 1, that means x is replaced with minus x, then it reflects the graph of function across the y-axis. For example, say you're given this curve y is equal to root x, then if I multiply with a negative sign here, then the graph is reflected across the x-axis. Okay, because for at any point x, instead of getting root x, I am getting minus of root x. Okay, so the graph is reflected along the x-axis. And if I replace the x by minus x, okay, then the graph is reflected across the y-axis. Okay, so these are vertical, horizontal reflections and scalings. Uh, Finally, I define one-to-one functions, and then I will give you definition of inverse. Okay, so a one-to-one function, a function fx is one-to-one on a domain D if f of x1 is not equal to f of x2 whenever x1 is not equal to x2 in domain. Okay, so that means that if you have two different points in the domain, those two different points will always take give the two different outputs. Okay, then it is one to one, means two points in the domain, two distinct points in the domain cannot go to the same output. Okay, if they go to the same output, then we will not call it one to one function. Okay, so if you take any two points, distinct points from the domain, there by a function rule, this f of x1 point will give one value fx1, x2 will give one value fx2. If these points are distinct, then their corresponding outputs must be distinct. Okay, if that is true, the function is one to one. Then how to check whether the given function is one to one graphically is the horizontal line test. Okay, so a function y is equal to fx is one to one if and only if its graph intersects each horizontal line at most once. Okay, so because say given y is equal to x cube. Okay, so if this curve is one to one, if you move the horizontal line from say minus infinity to plus infinity, okay, vertically, this horizontal line move from bottom to top upward. At each point, if it touches the graph only one time, then this function is one to one. Like this y is equal to x cube is a one to one function because the horizontal line meets this curve uh, at only one point. Okay, everywhere. Okay, you move this red line from bottom to top, you will see that this cuts the y equal to x cube only at one point at a time. Okay, that means if you are taking two distinct x1 x2, their corresponding y values are not same. Okay, similarly y is equal to root x, this curve is one to one. Okay, so what curves are not one to one? Say for example y is equal to x square. Okay, so the horizontal line meets 2 points of the curve. Okay, so this function is not one to one. Okay, similarly this curve of y is equal to sine x. Okay, so at pi by 6 and 5 pi by 6 it gives the same value. Okay, so there are two different x values for which y values are same. Okay, so two x1 and x2 points are there for which fx1 and fx2 are equal. Okay, so this is not one to one. Okay, similarly here you can see that when x is -1 and x is 1, for two different inputs we get the same value of output, which is 1. Okay, so same height. So these two functions are not one to one, and similarly many more functions are not one to one. Okay, which do not satisfy this property. Okay, and immediately you can guess that all uh, even functions which are symmetric about y-axis, okay, they are not one to one, and all odd functions, okay, which are symmetric about origin, they are one to one. Okay, Finally, we define these inverse functions. Suppose that f is a one-to-one function on a domain D with range R. The inverse function f inverse is defined by f inverse b equal to a if f of a is b. Okay, the domain of f inverse is R and the range of f inverse is D. Okay, so if f is a one-to-one function, okay, from D domain to range R, then we can define the inverse function, and the domain becomes range, okay, and range becomes domain for f inverse function. Okay, so if f of a is b, then it means that the inverse image of b will be a. Okay, so f inverse b is a. Okay, so this is important, and the function has to be one to one. Okay, say for example, I say that if y is equal to sine x is this curve, then this domain is minus infinity to infinity, range is minus 1 to 1. It is periodic, that means it will not satisfy horizontal test because the curve is repeating. Okay, not invertible, okay, because it is not one to one in this domain. But then you know that the sine inverse x you have seen. Okay, so but domain restriction can help us in making a function one to one. Okay, so if we restrict the domain of a function, okay, so that it becomes one to one, then we can invert it. Okay, so domain restrictions make the trigonometric function and all other similar functions, okay, which are not one to one, we can restrict the domain to make them one to one function, and then we can take why we can calculate the inverse of that function in that restricted domain. Okay, so for example, see that this function from minus pi by 2 to pi by 2. Okay, for this curve from minus pi by 2 to pi by 2, okay, it is one to one symmetric about origin, and every horizontal line passes only at one point. Okay, so this from minus pi by 2 to pi by 2, this y is equal to sine x curve. Okay, so if we restrict the domain to this, okay, range is minus 1 to 1, then this is a one-to-one function, and so we can define the inverse of sine x, okay, in this restricted domain. Okay, so we can define the y is equal to sine inverse x function. The domain becomes range, so do this range is minus pi by 2 to pi by 2, and range becomes domain, so domain is minus 1 to 1. Okay, so in this restricted domain minus 1 to 1, or in this minus pi by 2 pi by 2, the sine x function is invertible. Okay, so for inverse of functions, you have to make sure that the function has to be one to one. Okay, and if it is not, then you can restrict the domain, and in the restricted domain you can invert the function. Okay, so this is all about functions, and in the next lecture we'll talk about the limit of a function of one variable.